Questions?
I have like a very basic question from the first class on designs. Like this, you told that in our sector, because we have integer modes of our size and fermionic things like TF, you have this psi equals psi tilde for Neumann and psi equals minus psi tilde for Dirichlet. And that's the only way you can. So I guess for fermions, the classification goes as follows: that you can either preserve TF at the boundary. First of all, what exactly is the condition for TF? You wrote, probably that was a typo, that it's TF at sigma equals 0 and pi 0 equals 0. Or it's like TF equal TF.
TF equal to TF.
Yeah, I guess
TF equal to plus or minus TF.
Then that was a typo. Yeah. TF equals to plus minus.
Yeah, it can be plus or minus because the x always has, suppose you have a normal model,
right?
Then x, the del x is equal to del pi x.
Yeah, right.
And then psi equal to psi tilde or minus psi tilde
because
depending on the NH or because of the NH or R.
No, because of the GS.
Because of the GSO meaning, the GSO allows you to do this projection, but whether you are using psi equal to psi tilde or psi equal to minus psi tilde, at sigma equal to 0, you always put the psi equal to psi tilde. Because one you can always change the sign, right? Then at the other end, we have two choices. One is psi equal to psi tilde, the other one is psi equal to minus psi tilde.
Right.
So minus psi tilde is NS and psi tilde is R.
Okay.
Right? So then TF you can calculate from psi del x, right?
Okay.
TF in the bulk is psi del x. Right? So then TF can be either equal to TF tilde or minus TF tilde.
Depending on, for R it will be equal and
exactly.
For NS it will be minus.
Exactly.
Negative.
But sigma equal to 0 n, they are always equal. So that's why we have chosen your definition that our sigma equal to pi n. Right? They can be either equal or unequal, depending on whether in the NS sector or R. If they differ by size, right, then the moding of the TF becomes half integer moding.
Right.
Which is what happens for NS.
Okay. Yeah.
Right? And the moding for in the Ramon sector, the moding for TF becomes integer moding. But if you change Dirichlet to Neumann, then this also gets reversed.
Yeah. Yeah, because TF has the del x.
Yeah. Well, actually, TF doesn't get reversed. TF has exactly the same property. Right? Because Dirichlet to Neumann, x also gets reversed, right?
So I can maybe just simply say that the NS is characterized by TF equal minus TF tilde at the boundary, and R is characterized by TF equal TF tilde at the boundary.
Exactly. Yeah. At the sigma equal to pi boundary. Sigma equal to 0, you put both equal.
Both are same. Yeah. R and N.
Yeah. Okay, so more the invariant set that TF will have half integer moding in NS.
But for Dirichlet, you actually do psi equal minus psi tilde at sigma equal 0 in NS.
Yeah, that is true. But del x is also equal to minus del x tilde.
Right.
So TF will be equal to TF tilde.
Okay. Oh, then probably I said the wrong statement. TF equal TF tilde at sigma equal 0 for both R and NS.
Yes.
And TF equal minus TF tilde for NS at sigma equal pi.
Yeah. And this is independent of Dirichlet Neumann because Dirichlet Neumann affects both del x and psi in the same way. You are switching the boundary condition, but on del x and psi simultaneously. Yeah. And this is also the reason why the ghost fields, for example, don't care about Dirichlet Neumann. Right? Their boundary condition is correlated to the TF boundary condition.
Right.
Because QB, the KB has to be constant.
Right.
At both ends. Right? So if TF equal to minus TF tilde, you also have to make sure that beta and gamma are equal to minus beta tilde and minus gamma tilde.
Right. So it's decided by TF in effect.
Yeah, yes, you can say it's decided by TF. Or equivalently decided by the boundary condition of the supersymmetric transformation parameter. Okay, great. Another question? Okay, so last time we discussed how to calculate the one-point function on the disk, but we said that you can only calculate the ratios of one-point functions. Because there is overall normalization which was undetermined, and that has to do with the fact that if you take your minus 5 and this. Okay, this problem appears also in the Mozart string theory, except that 3 minus 2 5 are there. So this can verify. So this has the structure, there is some constant k times 1 minus 2. And at present k is not enough.
Okay, just close it or yeah.
Okay, from whatever you have said so far, k is not determined because for bosonic string theory, for in the closed string sector, the C's and C bars are equal to minus 2 5, equal to minus 2 5 bar. That you could declare to be 1 because the normalization of C is up to you. Right? You could normalize the C's appropriately, so declare that to be 1. But once you have done that, you can no longer use the normalization of C as a freedom to fix. Right? So you need to find K. So we'll discuss how to find K. But let me just say at this stage that if you know K, then this in principle determines all higher genus correlation functions with boundaries. And the way you can do it as follows. Imagine that you have a Riemann surface and with some holes. These are boundaries. Okay. Now, if we didn't have boundaries, we already discussed earlier how we can determine the correlation functions on a higher genus surface in terms of a sphere correlation. Right? You just start with 3-point function and start doing. Right? Here, what you can do is that if we have something like this, you can think of this as having this boundary with a closed string and n. And some other Riemann surface. Right. So insert a complete set of states, phi r, phi r, c, as we did in the case of closed Riemann surfaces. So insert a complete set of states here. And so, and that, as we saw, corresponds to swaying this and Riemann surface together. Right? Yeah.
This is what these are disc.
These are discs. See, earlier we had taken a sphere with some punctures.
Yeah, and then glue.
And then a glue. Right? Here I am saying that you can do the same thing with the disc with the puncture.
Okay.
Right? You glue this with this.
Who is the boundary now?
Boundary is here. This is the boundary. This has a boundary, right?
Yeah. Okay.
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 So on the one hand, if you know this correlation function, you can perform this sum.
Yeah.
Right? On the other hand, this has the physical picture of this will be the Riemann surface with cube going into a disk. Right? A cube opening up into a disk. That's like adding a boundary, a hole to this Riemann surface.
Yes.
Right? So it is in this sense that in principle, if we knew the disk one-part function, how to normalize the disk one-part function, you can determine the correlation function on arbitrary Riemann surface with boundaries, because you can create all the boundaries by adding this disk with one-part function, disk one-part function. Right? However many boundaries there are, right? Each boundary you can replace we can do it to the Riemann surface by using this complete set of states. Is it clear? Right, so knowing A, so
Why do we not know K? I'm forgetting.
because this will on a this suppose you can calculate the correlation function on a disk, right? You can manipulate all the using computation relations etc. to bring it into this form. A set of C's and it will be minus 2 pi. But this you don't know about it. I mean we have not told you how to determine this so far, right?
It's probably, is it because the normalization of the BC host action? I mean that should completely fix this, right? But we probably
It should.
that's ambiguous or
No, it's not ambiguous because you have fixed that using the closed string amplitude,
okay.
right? So I'm not saying it's ambiguous. It's that we don't know how to do it yet,
Okay.
right? We'll determine this, but from whatever you have said so far, right, we have not said how to determine this, right? Because if you use just the usual computation relation, you can remove all the pair of BCs, right, by OP or other computation relation or OP, right? D with C has a singularity, so by looking at the singularities in D, you can write, suppose you have D, C and 3 C's, that you can determine in terms of 3 C's because you know exactly where the poles of P are, right? And you know that P has that correlation function has to fall off as 1 over Z to the 4 as Z goes to infinity because B has dimension 2. Using that, you can fix this in terms of 3 C's and it will minus 2 pi. Right. But this normalization we have not fixed.
And the reason is probably because we used this holomorphicity trick. Like we didn't do it like from.
Yeah, we didn't do a path integral.
Yeah, exactly.
Yeah, exactly. Yeah, we didn't do a path integral. In principle, path integral should determine this if we do define the path integral.
I guess and that it's probably related to those CD2 CH2 written in Polchinski. CD2 like
yeah, exactly.
Topology dependent
exactly.
fact prefactor.
Yeah. Right. So I mean he discusses even in the context of spheres, right?
Yeah.
But that's equivalent to what I said. Right?
Yeah.
You have a 4-point function on the sphere. You can write it as a product of your 2 3-point function corrected by this thing.
Okay.
And these other boundaries, right, in terms of moduli space, like pinching and so on.
Yeah, this is like pinching, right? Yeah, if you remember, the way you do this is that you identify W1, W2, but Q.
Yeah, and Q going to 0.
And this is equivalent to inserting this IRC U. Right, and then inside a phi r on this side, you are into the phi r.
Yeah.
You are into the phi s, right?
Yeah.
So this Q comes, so in the algebraic expression it comes because you have to calculate this matrix element.
Yeah.
And in the geometry it comes because you are identifying W or W equal to.
Yeah.
Is that clear? And that's how you make connection between the parameters that level the Riemann surface with the parameters that appear in the algebraic expression.
Okay. What is the connection with the deep brain actually? Like you have
Deep brain connection is that the boundary, whenever you are bounded, open string there, the boundary condition defines a deep brain. Right?
Yeah. Boundary is in a deep brain.
Yeah. Okay. So here, for example, in order to evaluate this, you have to put the boundary condition, right?
Yeah.
Whether the x has normal or is the boundary condition.
Yeah.
Right? You have to specify it for each one of those. So that's the information about the deep brains.
This is actually like, this is a Riemann surface of what closed strings, right?
No, but I'm not inside the vortex operator.
Yeah.
Right? The vortex operator you can insert anywhere. I mean, you can have closed or open string, right? So vortex operator should be these are the closed string vortex operators, and these will be the open string vortex operators, right? On the boundary you can insert open string vortex operators.
Okay.
C and this is O.
So when you have both open and closed strings, in general, you will have something like this.
Exactly.
Without the boundary.
Yeah. When you have a one surface with boundaries and holes and handles.
Yeah.
Right? And if you have external open and closed strings, you have to calculate something like this. Okay, but all of these I am saying that you can get from by glue.
Yeah.
All that will happen here. I mean, if you have something like this, then you also have to have these functions. Right? So far this. But all of these are determined once you can determine k, right? So k, of course, will depend on what deviation you have, right? What boundary condition are put on this. Different deviations will have different k in general.
Yeah.
Okay. So for every deviation, you have to determine this k once and for all, and then you are done. Right? Then you can use that k to calculate the amplitude as well. Is clear? Now how do I erase the whole thing?
There should be a new page.
There should be a.
It's at the end.
Yeah,
Bottom right.
Oh. New page.
Yeah, or you can go back
Okay.
and this is to add a new page.
So for this, we start with what we know, right? That we can determine the ratios of the couplings. Right? If you calculate, for example, this one-part function, you do not know the overall normalization of the graviton one-part function or the electron one-part function or the RR field one-part function, but the ratios you can determine, right? Because k is one overall constant that we have. So using ratios of one-part function, you can okay, so let me write down what effective action one gets for a T different. So the result is constant T equals minus equal to x parallel with the parallel denotes the coordinates along the direction, along the different
World volume.
around the one volume. Yeah. E to the minus I x parallel x parallel below. And then we also have counting of the point integral plus 1 0 1 plus 1 1 2 yes. So the calculation I have described so far, okay, of course, doesn't determine the full structure. Because this depends on the one constant, right? This is determined from the one part function of the C, of the rubber field. This one, the part that will determine, and that's what all you need for this, is integral. I have written down the whole answer, but it's not, as I said, one part function can only determine something like this, minus phi. Okay, which is the expansion of this to linear order, right? H mu nu is basically G mu nu minus n. Okay. Because if you just expand this out, right, the one part of course is just a standard constant. Okay, but you will get a minus phi and then half WH mu nu from the square root of it. And T is unknown, T is known in terms of T. I think there is one minus sign here because in the action the potential energy term is negative, right? So P is the tension of it. Okay, physically it is the energy per unit area, per unit P volume, unit energy per unit P volume of the P.
You just linearized it, right?
I just linearized it, right? And what I am saying is that the one part function calculation only determines the linearized part of this act, right? But the full nonlinear analysis tells you that this is the point. Okay, up to hard element, right?
For that, what you compute 2 point.
Yeah, you calculate multi-part function and then you have to use various arguments like symmetry arguments and so on.
To say that this is the only form.
Yeah. I mean, this part is clear, right?
Yeah.
By general coordinate, yes. Whether it's to be minus phi or some other function of phi is not clear, right? So, the fact that it's to be minus phi that you can argue from other considerations.
And that's why this is called tension, because analogous to string, like
Exactly.
1/4 pi alpha prime.
Exactly. Yeah.
Alpha prime was the inverse of tension.
Exactly. Is there?
We still haven't calculated K, right? So
No.
still don't.
Yeah. So you have to calculate T, equivalent T, right? So this is what you have to determine. So the way we will calculate this, calculate T, is that we will try to calculate the effective interaction energy between two deviants, say one placed at 0, one placed at some point r, using two different methods. One is what we can call closed string exchange, which is that these phi, so this tells us that this deviant acts as a source of phi and h, right? And C.
Yeah.
Okay. So because they act as a source, okay, and we know that phi and h are like lossless fields, right? So if you put two deviants at far away points, okay, there will be an interaction energy due to the exchange of the lossless. Okay, that you can read out from this action. That will involve P square, right? Because two deviants placed, right? That will involve P square, and it will involve the propagator of the lossless.
Yeah.
Right? The Green's function for the lossless field, which you can calculate. So that gives you one way of calculating the interaction energy between these two deep ends, right? Two deep ends placed at some higher points. The other way will be using the open string channel, which I'll describe later. Right? But first, let's see how to do this in the closed string channel.
Also, you have converted this determination of K to determination of T. Okay.
And if you can determine T, we determine Q. Right. Plus T is given in terms of T. We take parallel deepens. Parallel deepens. One place that is part equal to 0. Other one is part R times something hat. Because the direction of the inflection really doesn't matter because of the rotational invariance that transfer states. What is important is R. So in this case, the relevant part of the action goes to the action. Again, if you look at the full interacting part, okay, that has a structure like basically integral in x pi over G R plus 4 and then there is another term which is C. Okay, so there is this is the action involving the graviton and dilator. Okay, again, this is the full nonlinear form of the action up to two derivatives. But what you need is only the quadratic part of this action. So we don't really need the full nonlinear part. This is of course already quadratic.
This is F square.
This is F square, yeah, the kinetic property. Clear? So this I can formally write as I'll write in the next slide. So we linearize. Linearize the field equation is the quadratic part of the action. So these are the structure of integral dkx. Let me write here h I. Then some kinetic term, kinetic power is a matrix. Onto the operator. plus so the call is the inner sector. This is inner is the RR. Okay, and you are assuming that there is some gate fixed. Then the final answer doesn't depend on what gate you have taken, but you have assume that you have made done some gate fixing. Okay, so that these are irreversible operators. And then we have the coupling, which is of the form E and then we have phi of x minus phi of x plus of h plus, or I should have put some just one factor. And yeah, you can correct, I think it's too complicated. Yeah, here there's the distribution down or what p plus two factor because it's totally antisymmetric to the is then yeah, this should have been 1 or p plus 1. Only contract yes, you get p plus 1 factor there. Anyway, the details do not really matter. I think I'm not going to do the calculation as such. 1 over p plus 1 factorial. Epsilon plus 1 p yeah, so this is the kinetic term for the massless closed string fields, and this is the linear term. Okay, this is a linear source, so this is like a source for the closed string fields.
What happened, by the way? I mean, you have added this.
I have added, yeah. So the added meaning these of course they are right. The closed string effective action has this term.
Yeah, but what is the last?
This one, this is source term. This is what this is that term. What we got in the presence of deeply dead, right?
Okay, the other action, the world volume action.
Yeah.
But you are now writing it on full NP space.
Yeah, okay, delta.
Introducing delta.
Exactly, right? Here you are sitting in the around the wall volume direction. Now we are full writing it and for expand, right?
Okay.
What we are going to do is to construct the effective interaction between the DP branes by integrating out the closed fields. Right? So in terms of path integral, you have e to the minus s times the integral over the h and phi and c.
Yeah.
Okay. So you can do it that way. It's a quadratic action anyway. But you can also think of this as a classically eliminating h and phi using the linearized equation. Right? Because this acts as a source.
Yeah.
Okay. So you integrate out closed fields.
What do we want effective action for?
On the 2D planes.
2D plane.
Yeah, one at 0, one at r.
Okay.
And the other is interaction energy or interaction energy density. Yeah.
But you are saying C is not closed string field somehow.
C is.
So we integrate out everything.
Yeah. Integrate out C and H and phi.
Okay.
We integrate everything, right? But we keep them separate. We can separate the contribution into a NSNS contribution and R contribution, which you can do, right? Because there's a cross term between C and H and phi. H and phi may have cross terms, right? But C couples only to C, right? There is a two-point function between Raman field and the NSNS.
Right.
Yeah.
Direct terms are separate. So you can integrate separately, then you can. So now you are going to integrate out everything, but keep the contribution separate.
Usually in QFT, like if you have a source turned on some J, then you integrate out the phi.
Exactly, that's what you are doing. Right?
Here, where is the J?
J is this. This is our J.
Oh, okay.
Right?
Oh, this is linear phi.
This is J. Yeah, this is the linear term in phi, right? So this is roughly our J. This is J. Right? So J has a sum of two terms. Okay, and this is a J for both, phi, H as well as. Right? So you could have written separately as J phi, J, and J. Okay? So you can write this as J phi, J, H. So you have integral phi. This will give you exponential integral of integral. Okay, so G is the two-point resistance. Again, this has separate RR component, right, which is the CC Griggs function, and then the NSNS component, which is the phi H Griggs function, right? In the way we have introduced phi and H, the kinetic term may have off diagonal terms. Okay, that will be phi H coupling. That's why I am not separating out the phi and H separately. But NSNS and RR can clearly be separated because there is no mixing between C's and the RR fields and NSNS fields at the level of the two-point function.
J will be some delta function.
Yeah, J is some data. Yeah, each J is a data
Sum
function.
of two delta.
Sum of two data functions. So one thing is clear that that will restrict the x integrals into only the integral of the parallel direction. Right? X and x prime both integrals will restrict to the parallel direction. Okay. Now J has sum of two terms, but two of those terms which are the diagonal ones.
Yeah, we want off diagonal to get the.
Yeah, we want the off diagonal one because we want the R dependence, right?
Yeah.
The diagonal ones, right? Which is x part equal to 0 with x part equal to 0, and x part equal to R with x part equal to R. Those don't have R dependence. Okay, so you look at the off diagonal terms. So off diagonal terms, the R dependence terms. Roughly we have the structure. So half will go ahead because there are two off diagonal terms, right? 0 with R and R with 0. So because we can be I minus 2 orders. Key of x squared equal to 0 prime plus and then there will be t square. And there are other factors on the way, factors of 2 etc., which will not worry right now. But this thing will be given by t square. We'll have multiplied the factor of t square. And G will have two pieces, NS and RR. Yeah. Okay. Now this will depend only on the difference between x prime and x. Okay? Just by translation difference along the plane order. So we can separate out the integral around x part integral, and then we can change variable x prime part equal to x part plus some y part. And the non-trivial dependence is only coming from the y part. Is it clear? That this depends only on the difference, right? By translation invariance.
One thing, like, what was the off diagonal part that I couldn't understand? Like, this J will have two terms, delta at x perp equal 0 and delta at x perp equal r and
exactly
n perp.
So you look at the cross term between 0 and r.
Why not the RR term?
Because that is independent of r.
How?
Because if both are at r, right?
Because G will
depend on the difference.
Okay, and that will be 0.
Yeah, so that's basic, right? So if both are at r, then it has no r dependence.
And you're saying now that G, like when it's non-zero, it will have NS, and RR.
Exactly. It will have separate NS. NS will come from the H and phi bits function.
Right.
And the RR will come from the C bits function. Right? So basically, all of them are just inverse of the Laplacian in 10 dimensions. Right? That's all are massless states, right? So there will be some numerator factors which you have to diagonalize. Otherwise, the main content is 1 over Laplacian, right? Which you know what it is. Then you know in momentum space, you know in position space. So that's how we have all the This is here. So at the end, you will get something like exponential. Well, I'm not being very careful about the signs. Plus 1 x bar. All it is one. So what I've done is that I'll use the fact that G is transversal invariant. I'll use the fact that G is transversal invariant to set x bar equal to 0.
X parallel. No.
X parallel, sorry, x parallel equal to 0. Because it depends on the difference, right?
Yeah.
Okay. So in other words, the difference that if you change variable to x parallel and y factor, where y parallel is x prime minus x.
It only depends on
The difference.
x perpendicular minus x prime perpendicular, right?
But also the x parallel minus x prime.
Yeah.
Because you are doing separate integral from these two, right?
Yeah. This side.
Suppose here the point is here, and there the point is there.
Yeah.
Then even the x parallel difference will contribute, right? Let me write. Suppose you have these two planes, right? So one point is here, another point is here. So this is x. This is the r. This is r infinity. This is r. This is r in alpha, right?
Yeah.
This one, what I find calling y path. So this Green's function will depend both on this and y path.
Oh, you are saying instead of integrating over here, you put it to 0 and integrate.
Exactly, that's right.
Okay.
Because then we are simultaneously integrating over both.
Yeah,
Right?
yeah.
Of which one integral is trivial.
Yeah, yeah.
Right?
Yeah.
That's the volume integral.
Yeah.
Right? Nothing depends on that volume. Right? The other integral is what is the relevant one. Is this clear? So this is what I've done. Okay, one I've set equal to 0, the other integral is relevant one. And this simply reflects the fact that if you have two parallel planes, right, the action will be proportional to the wall volume of the plane. Even if a static plane, right? Its action is proportional to its wall volume.
Yeah.
Right? Because it has some mass per unit area. Right? So you have to integrate this over the whole area of the plane, and then you have to integrate over time. Then the action is also time. So that's why this integral basically is reflecting that. This is a non-trivial quantity integral.
Oh, right.
Okay. Now, as I said, G is just a master Green's function. So this y parallel integral you can certainly do easily. Yeah. You can do it either in position space or you can go in momentum space and do it. Yeah. Okay. Either way, this is a known integral, and this will give you some function of r. So effectively, this will reduce to. I'll give the result. I mean, it's clear from the. It will reduce to this whole thing. It will reduce to e squared times a constant c R for 9 minus P. Where this is the same P like here. This is a numerical constant that you can have.
Where is the world to volume?
Pardon?
World to volume.
The factor
It is in the
VP
C.
plus 1.
Yeah, this times the integral.
Oh.
This will be common to everything, so you don't really have to worry about this too much.
X parallel.
X parallel, Y parallel. Oh, sorry, X parallel. Yeah. Y parallel is okay. C can be computed because we know G, right? This part, okay, of course you can do this calculation and check that this part is the correct one. But this is basically you can guess what this part is because 9 minus P is the number of transverse sections.
Yeah.
And the interaction energy will be the 1 over the number of transverse sections minus sign. The interaction energy will be the 1 over the number of transverse sections times the minus 2, right? If you have 2 point particles, right, in 3 dimensions, then number of transverse sections is 3, right? The Coulomb interaction energy is 1 over r. Yeah, so 1 over r to the 3 minus 2, right? So if you have 4 space dimension, then it will be 1 over r square and so on, right? So that's this r to the power minus 9 minus 2 minus 2.
But for D1, D0 is the point particle, and you want in 3D it's 1 by r, and in 9D it will be 7.
Here we say, yeah. Okay. So the point I wanted to emphasize here is that we can calculate this interaction energy in terms of P square. And you can do it separately for the NS-NS exchange and the RR exchange. The reason that it's important to keep this, do this separately is because the NS-NS and RR exchange actually cancel. And that happens because of supersymmetry.
But G had 2 pieces, one from NS,
One from RR.
then
Right? So those will cancel. So if you calculate
0.
Yeah, if you take the sum, then C is 0. Right? And that is basically, as I said, it's a reflection of supersymmetry, and it is saying that if you have 2 supersymmetric rings, right, then they have the attractive gravitational force and related exchange force, and that's the repulsive gauge force because they have the same charge, right? And those exactly cancel for supersymmetric rings. So you don't want to sum them, right? We have to keep them separate. Okay, separate contribution from NS-NS and separate contribution from RR, and you have to extract these contributions separately from the other calculation. Is this clear? So this tells you how to calculate the interaction energy using the closed string channel. Think of the interaction energy as coming from the exchange of closed strings between 2 deviates. Now we are going to calculate the same thing, but from the open string channel. Okay. So first let me explain what exactly one means by open string channel. And so for this it will be good to have a pictorial representation of what we are actually calculating. So let's imagine that we have 2 deviates like this. Okay, so this is at 0, this is at r. And what we have calculated here is the effect of exchange of closed strings between these 2 deviates. Pictorially, you can think of this. as a closed string extending, getting extended between these two difference, right? Right? It just so happens that when the distance is large enough, then only the massless contribution is important. Right? That's why you will look at the massive exchanges. Because massive exchanges will follow exponential minus.
Oh yeah. This is
right?
a power law.
Yeah, because you are taking the instead of part, so you are taking the distance to be large enough so that basically you are going to look at R infinity. That are large limit in which all the massless contributions or the massive contributions. Okay. So a closed string gets emitted from the first difference and gets absorbed by the second. That's the exchange that you are talking about. But now you see that this exchange, you can also think of this as an open string propagating in a loop. Imagine that this is the open string. Take a section. Right? Then for each section you have an open string. With one end on this ribbon, another end on this ribbon.
Yeah.
Let me draw the open string. So this is the open string. That's the open string. And this open string is propagating in a loop. As you go around the cylinder. So closed string is when you are thinking of this and the direction in which the string is propagating. Right? In which case the string is closed. Open string is when you are thinking of this as the direction in which the string is propagating.
There was the open string to start with between these.
Yeah, the same diagram, the closed string exchange diagram, can also be thought of as an open string loop diagram.
It was fine actually. This guy emitted a closed string and it propagated and
Yes,
it was absorbed.
true.
Open string, what was it?
Okay. Let me draw this. If I didn't draw that a little easier. You take two digits. Okay, think of this as space and time. Okay? Now, we create this is an open string.
Yeah, at some instant of time.
At some instant of time, some open string at some instant of time. Now imagine that we have a loop of the open string getting created and getting annihilated. Right? A pair of open strings getting created and getting annihilated.
Okay. Then it is like something like
Yeah. So you start from here, so there is an open string, right? Then it start getting separated and then come back and be together, right? Okay, so that is like a vacuum diagram of the open string, right? It's getting created and destroyed, right? So in terms of Feynman diagram, you think of this as a bubble. Right? Normally you don't include these bubbles. Okay, that's a normalize, but in string theory you don't always normalize, you can include these bubbles. Okay. So this is what you are doing, right? This thing is propagating in a loop. Propagating in a loop, and after that you have this cylinder.
It's the amplitude, like if you calculated this way.
Yeah, so the amplitude better be the same. Because the same diagram can be regarded in these two different ways. Right? One is as the open string loop, other one is the closed string exchange. Right? And this is very common in string theory, right? I mean, this is the reason, for example, the 4-point function, you can decompose in the S channel, T channel, U channel, all of these give the same. Okay? This is just a version of that. Right? You can, given a worksheet diagram, you can reinterpret this many different ways. And they better give the same result. Is this clear?
okay.
So let us see what kind of contribution one expects, right? And for this, let's just use the QFT intuition. So in QFT, one loop toggle come from this is a standard architecture. Imagine that you have a site. Suppose you have a action. I box box so we get integral d psi exponential integral equation in plus d space standard I of minus a. I'm not being very careful about the signs, etc. X. So this is like for every psi of k, you'll get k square plus m square to the minus half.
Yeah.
Right? Because psi of k is a bosonic plane. So this gives you
This is sum over all the vacuum bubbles.
yeah, unless they come, yeah, some overall vacuum of exactly. That's why you have the exponential.
Yeah.
Right? Otherwise, you'll have just one vacuum bubble is what is appearing in the exponential.
Yeah.
Right? But in the exponential, you get some overall vacuum bubbles. So that's the very vacuum bubbles. So this is a write as exponential right? So for graphs on odd fields, let me write the not for fields but just for graphs on odd variables. Exponential this is antisymmetric. Okay. Then this gives you Ophian of A, which Ophian phase is roughly determinant of A. Right? Like if you have d psi 1, d psi 2, potential A1 to psi 1 psi 2, like you get the result A1. That's the Ophian of the matrix. And this is the matrix, which you can also think of the determinant of the square root of the determinant of the matrix. So this, if you compare it with the earlier bosons, this is exactly. If you compare this earlier example of bosons, right? This was like determinant to the minus half.
Yeah.
Determinant of the operator minus half, now we are determinant of operator to the half, right?
Yeah.
That's the refinement formula and bosons. Is it clear?
Yeah.
is 1 in this side of 1. So the net result of in the integral, so net result of in the cos integral I can write as exponential of minus half a square plus m boson square or a square dot. And it is trace log so here to think of the m e square and m f square as the mass square matrices. Okay. We don't have to assume that mass square is diagonalized, but I mean typically you can always diagonalize the mass square matrix, right?
Oh.
So trace log means what? They are just summing over all mass, all fields of all masses.
No, because the mass matrix is not diagonal, you are saying you are taking that.
I'm writing it this way, but I mean we can always diagonalize the mass matrix, right?
Then there is no trace.
So there is still a trace. Trace means you have to sum over all both.
Oh, okay.
Okay, that's all. So you can think of the mass matrices as diagonal, but you sum over all bosons, and you have to take the also sum over all formulas
Yeah.
with a minus. Is that clear?
Yeah.
So this is the structure of an exponent. Okay. So log of bosonic contribution minus log of harmonic contribution.
Trace you have written because M can be a matrix, you mean.
Yeah, I mean you can take a diagonal matrix, right? Imagine the name is a diagonal matrix. Yeah, we have still some over it. For formulas, the point is it's not. Okay, M can be off diagonal, M square can be diagonal, but M is off diagonal. But what this means is that you are just summing over all bosons,
Yeah.
and all formulas. Right? That's all it means. So I'm just trace as a formal operation. Okay, now we are going to rewrite this in a slightly different way. And we'll rewrite this using following identity that if you take log of H1 minus log of H2. This I will write as integral go to infinity. Okay, let us try to prove this, that this is what you get. So because you are taking the difference, right? This is a well-defined integral. Okay. And t equal to 0 that's a singularity. Okay, and t equal to infinity also that's a singularity as another h1 and h2 are. What's this? So this one I can now write as minus integral epsilon to infinity dt over t. And then take the epsilon goes to 0 limit at x. Right? This you can always do. But what you can do now, okay, is that once you have written for epsilon to infinity, individually these don't have a singularity at t equal to 0. Right? Because t equal to 0 is outside the range anyway. Now you can change variables here as well as there. So I change variable to h1 hip equal to y or so this gives you minus integral u1 over u1 minus u1 minus integral over minus only difference between these two integrals is the lower limit. Right? So t was epsilon. Right? So u was is h1 epsilon. Clear? This I can write plus minus h1 epsilon h2 epsilon. Right? Because u1 and u2 are just declared as right? Both are finite integrals and take the difference. The only difference is between these two integrals is the lower limit. So I can just write this from h1 to h2.
E to the minus two.
But
E to the minus two.
5 to the minus. Right? Okay. But now if you take the epsilon goes to 0 degree, right? Then you see that u is range restricted to a very small range, right? So e to the minus u can set equal to 1 as epsilon goes to 0.
But epsilon to 0 is like, it looks like 0 actually because upper and lower.
Looks like
0 because both the upper and lower limit are.
no, it will not be 0. H1 to H2. This H1 is at H2.
Yeah, but epsilon going to 0 both are.
Right? So this I can approximate. Integral epsilon 1 epsilon H1 epsilon H2 d1.
Because u is very small in this. No, e to the power minus u is small.
Yes, e to the minus u I am ignoring because u range of u is very small, right? You are integrating from H1 epsilon to H2 epsilon. You can do a partial expansion. Right? And you can check the one term contributes. Right? The minus u term kills the singularity. Right? And then this difference is just proportional to epsilon. The epsilon goes to 0 that way. Right? So this gives you minus H1 current. So minus log of H1 current. Is log, right?
Plus.
One
Plus.
Yeah, minus will go away if you are writing h1 in the numerator.
minus H2 over H1. Yes. Plus. That's why we start. Okay, log of H1 minus log of H2.
Yeah.
Then is given by this. And so this is a two formula. Using this, we are now going to rewrite this expression over here. Before you put traces, right? And here we are going to make use of the fact that the final integral this is something that of course one has to check. Okay? That the number of bosons and number of formulas are equal, right? So the the integral will be actually finite. Okay, this you can check for the part. This is true, in fact, even if there is no supersymmetry. we will write Z as this is basically after summing over all these things, right? If you look at the identity over here,
We have
oh, somehow
momentum integral being missed.
trace will include a momentum integral.
Okay,
But I am not finding the
This
yeah, this one.
No.
Momentum integral now I am also including the trace.
Okay.
So this is you can include in the trace. So this trace includes momentum. Okay. And you see that at this level, right, as long as there is no divergence, as t goes to 0, we can rescale t in any way we like. Okay. So I can by rescaling t, because dt over t is invariant on a scaling up. Okay. So I can put an alpha prime here if I want. Okay, just redefine it.
But it's crucial that number of boson equal number of fermions.
Yes, it is that is crucial. Otherwise, it will diverge as t goes to 0, right? So that's the case. That the final result that we will get shouldn't diverge as t equal to 0. See, if the number of bosons and number of fermions are not equal, then this will diverge, right? Because there will be one extra come. Suppose there is one extra contribution here compared to this. Then as t goes to 0, there is non-zero contribution left over. Right? So the integral has to vanish as t goes to 0. Right? This is a consistency. So this I can now write an exponential integral 0 to dt over 2 times super trace why L0? Because you know that L0 has exactly this structure.
Yeah.
Right?
Yeah.
For the open strings, right? L0 of the open strings, ultimately L0 equal to 0 gives the on-shell condition, right? So L0 is alpha prime times k square plus n square. Is that clear?
Yeah.
And this trace, this super trace basically means that it's a trace with minus 1 for polynomials. But this is something that you can calculate from the open string spectrum. Right? You have two difference. Right? Open strings going from one different to another different. Right? That you can also have open strings from one different to the same different. But those are not going to be R dependent. Right? So those you can forget. Right? So relevant one is the open string going from the one different to another different. So that spectrum you can calculate, that L0 spectrum, because you know how to calculate the open string spectrum. Okay, so and hence you can calculate this. Okay, so this is some known function. This is clear. The only subtlety, okay, that you have to keep in mind, that I have to explain very well, is that when you calculate this trace over all open strings, you have to put a restriction that this trace is taken over trace. Because first of all, you see, if you didn't impose this condition, then the result would be trivially zero. Right? Why? Because take a state, right, which is not analyzed by B0. Apply B0 on that state, and that will have exactly the same L0 for opposite statistics. Right? So that will automatically give us zero. Right? So the way to understand this from the baseline perspective is that when you calculate this determinant, right, the determinant has to be calculated after gauge fixing. The gauge fixing basically restricts the open string states to B0 acting on the static condition. From the worldsheet perspective, right, you will interpret this in terms of worldsheet. From the worldsheet perspective, the reason that you have to impose this condition is because there are zero modes of B and C on the animals. Okay, so this is a cylinder, right, which is semi-animals, and there are E equal to constant is a zero mode. Right? C equal to constant is a zero mode. Those satisfy all the boundary conditions. Okay? So those you have to factor out. Right? And that when you try to reinterpret this as a sum over states, yeah, that subsets to this condition.
Oh, it's probably we have to saturate them.
You have to saturate them.
We have because we have global fermionic zero modes.
Exactly.
That's why we have to saturate them in the path integral. So I guess this is written as this B0 C0 in the
Exactly. Yeah. You can also write this as C0 B0 acting on the static point 0.
Yeah.
Right. Inside a C0 B0 inside the path.
Yeah, C0 B0 with a probably -1 to the F as well.
-1 to the F, yeah. That is automatic because once you put the periodic boundary condition on the formulas, right? The -1 to the F will come automatically because that trace that path integral periodic boundary condition on the graph for not variables is equivalent to calculated trace of -1 to the F.
Okay.
Right? The formulas are automatically weighted with the minus. Okay, but let's first try to figure out the R dependence. Where is the R dependence going to come from? Okay, because that's what you want to extract first. Right? So the R dependence, in fact, is because L0 has R dependence. So L0 has R dependence. From the mode expansion. When you see the X part, you will have a term which is sigma over phi n hat and sum, and then there are all the other aspects. Right? This is what you guarantee that at sigma equal to 0, X part is 0, and at sigma equal to pi, X part is n hat and sum. So there is a term like this, and this translates to is L0 Q naught R square plus R. There is some constants. That is the calculate. Is that clear? Okay. So you are going to, of course, you can calculate it by going through the whole procedure that I described earlier. Right? But you are going to do a shortcut and you calculate it. So to make a shortcut, recall that the condition in L0 there is an alpha prime k square 0 k r square. We have so L0 has an alpha prime k square. By this construction there is C0 r square and then there are other conditions, right? Plus oscillator. And this is equal to 0, which is the on-cell condition. This is on-cell. Right?
But why do we need on-shell condition?
No, we are not imposing on-cell condition because it's a loop off-cell thing. I'm just going to determine C0.
Yeah. Oh.
Right? So determine C0, you note that this is the on-cell condition. Right? I'm not going to make use of this.
Okay.
Right? Because otherwise the exponents will be 0, right?
Yeah. Yeah.
We have exponents minus k square plus m square. Those will all be 0 on-cell. Right? So you are not going to use this, but let's just forget about the calculation. I say that let's just say that if we are want to impose the on-cell condition, that this is the condition that right? Now this is by definition minus alpha prime m square, right? Because k square plus m square equal to 0 is the on-cell condition. So this tells us that m square is 0 r square on-cell condition again. And for large R, this is the dominant configuration. Okay. Now let's see what we expect for the mass of the open string for large R. Can you guess what is the expected mass of the open string if R is very large? Two regions very far, open string hanging. Okay. What is the expected contribution to mass square mass? Which is the R dependent, right? For large R. But C0 you don't know. We have to calculate C0.
You know what tension or something?
Tension
Yeah.
of open string.
Yeah, the tension of the open string times the distance, right?
Yeah.
Tension by definition is the mass per unit length.
Yeah.
Right?
Okay.
So expected here, expected M,
Alpha prime R.
expected M, the tension is 1 over 2 pi alpha prime, right?
Okay. That's how.
So this tells us that C0 R square is
You got rid of one alpha.
The alpha prime.
right.
Alpha prime.
The other alpha prime. C0 R square is alpha prime and it's 1 over 4 pi square alpha prime. Right? So this tells us C0 is 1 over 4 pi square.
Is clear? What about these other terms in the equation?
So other terms are the oscillator contribution, right? But for large R, this is dominant, right? Because this fact that the tension is Alpha parameters are, we are ignoring all the fluctuations, right? Otherwise, they will also be fluctuation. In the larger limit, this is the result. And because we already know that the form is this, right? This is not, this is for all, right? So then this allows us to determine C0. So now let's go back there. In this e to the minus t L0, the R dependent term would be e to the minus t times 4 over 4 pi square alpha prime times R square. Right? So that you can take out of the trace. Right? Rest of the contribution in the trace is R independent.
Yeah.
Because those are only sensitive to oscillator contribution. So you can rewrite this. And this 2 will also go away because there is open string has orientation, right? You can have open string going from 0 to R or from R to 0.
Yeah.
Okay, that will cancel this 2. So the final form is Z is equal to exponential plus dt over p for minus p r square 4 pi square alpha prime and some function of p that is R independent. Okay, it comes to the open trace over open string states. Okay, this you can think of this as just the standard trace without any R, right? No stage. So this is known. Now from this integral you see that if R is very large, then the contribution to this is going to come from the small t region.
Yeah.
Because it is exponential subtext, right? So that means that you need to know f of t for small t. Is that clear? Yeah. So for large R, f of t for small t. And let's suppose that this is given by some b naught beta, where b naught and beta are known. Okay, because f of t is known, so you can calculate how it behaves for small t.
So one thing about f of t, it's just the open string. It's just the annulus corresponding to from one brain to the other.
Yes.
But you were saying that it's almost as if because you have taken R dependence out, it's almost as if it is like the two brains are coincident.
Exactly.
But still, I mean, there can be there will be some open strings which are not stretched and
yeah, those are not R dependent.
yeah.
So that's like in the earlier calculus, if you remember, we had the two sources, right?
We didn't consider closed string from one to the same
Exactly.
brain. Okay,
Yeah.
okay.
Right.
So that's why we are not.
Exactly. Right. So those are R independent. So you are just comparing the R dependent contributions on the two sides. So this is clear. So now you substitute it here. Right? So you get Z equals to exponential of integral minus p r square 2 pi square alpha prime naught. And now you can define E equal to U times 4 pi square alpha prime over r square write this exponential. So dt over t becomes du over u. This becomes e to the minus u. Only this dt to the beta will, when you write in terms of u, will get some value. So we get 4 pi square alpha right r square. Yeah, it's some gamma function. Because this is some known object, right? E0 is known because we got it by expanding this known function near t equal to 0. And here we see some r square dependence. So this exponent is what you have to compare. This is what you compare. And dependent on t square. Right? So first of all, the consistency check is the r power should match. And this determines t square. This is t square.
So this gives open string contribution to T square.
This is the open string contribution, but the same thing can be reinterpreted as a closed string exchange. Right? So it is true that this is the open string contribution to the interaction energy.
This is same as what we did for the closed string.
Exactly. Because it's the same wordsheet data. Right? We have calculated the same wordsheet contribution, but now reinterpreting this as an open string channel.
Okay.
Right? And that's what allows us to determine T in terms of all these constants.
Why did we do this? We are happy with closed string, no?
So we have to determine T now. The T was unknown, if you remember. Yeah. Right? Now we have got a different calculation which doesn't depend on T. This fixes the constants, right?
The latest is that the open string thing does not depend on t.
Yeah, for open string calculation, we don't need T, right? It is just a internal spectrum.
R dependence in that case was some 9 minus p minus.
Exactly. So it will come out exactly that.
Beta should be
Right? The other thing is, if you remember that calculation had an integral over the x parameter, right?
Yeah.
This you can have square in there, that integral going to come. Right? That integral will come because when you calculate this space here, right?
the momentum.
Yeah, there is momentum.
Yeah.
Integral, right? Because open strings are carrying momentum along the parallel direction. So that density of states has a d, right? The integral, the momentum integral becomes is d times integral d p plus 1 k over 2 pi k p plus 1. So that's where that d will come and it will cancel against that integral dx, the dp plus 1 x parameter that will happen.
It is clearly that's the exponential of 1 by r squared to the power.
Yeah, here also it was in the action it was exponential. We calculated interaction energy in action, but in the partition function it was exponential, right? So they compared it to exponential. Okay, so there is only one more subtle point that we have to keep in mind. Okay? That if you do this calculation, the result is 0 because it was also 0 on the closed string channel, right? Because Ramon and Revusu are cancelled, right?
Yeah.
So you have to extract from the open string channel some more separate contributions in the Ramon and Revusu, right? Okay. This clear? Okay. So that let me just describe how that comes and then stop. And that actually you can see from the picture. Here is a cylinder diagram. So from a closed string channel, what is the difference between Ramon and NSNS? The difference is that for the NSNS, you put some antiperiodic boundary condition in this direction.
Yeah.
Right? For the Ramon, you put periodic boundary condition on the partners. Right?
Yeah.
Now, let's look at it from the open string channel. Right? What is the difference between putting antiperiodic boundary condition in this channel and periodic boundary condition in this channel?
Yeah.
Antiperiodic, normal boundary condition would have been periodic. If you just do path integral, right? You put periodic boundary condition on everything. But periodic boundary condition, when you try to reinterpret this as a trace, right? It is trace of -1 to the f.
Right.
And antiperiodic is not introduced. 1. So NSNS plus RR translates to 1 plus -1 to the f in the open string channel. And what is this from the open string group 1?
Some of
This is a GSO projection,
Yeah.
right? So what you have to do in the open string channel, right, when you do this calculation, is to not use GSO projection. You separately calculate the contribution from 1 and -1 to the f. So you take the trace in the open string channel. Trace has 1 plus -1 to the f. That is the complete trace.
Yeah.
But you can calculate separately the contribution from 1 and contribution from -1 to the f. Yeah, because you know the full spectrum.
Then you don't like look at states that are GSO invariant. You consider everything.
Yeah. So when you do this calculation, you consider all the states. Okay? See, the GSO projection you can think of as you first consider all the states, and then you apply the projection of what 1 plus -1 to the f.
Yeah.
Right? Now you are saying that that is the final complete answer.
Yeah.
Right? And that is 0.
Okay.
But you can take that complete answer and you can ask what will happen separately. You can calculate 1 and -1 to the f. Those will correspond to the NSNS and Ramon exchange in the closed string channel. That's how you extract tensor, right? Because in bosonic string theory or in non-supersymmetric this problem is not there. Because they are the iso cancellation, right? So you can do the whole calculation and determine the tensor once and for all. Right? It's only for supersymmetric brains that if you just do this calculation naively, there is a cancellation between the NSNS and RR exchange. Right? So that's why you cannot calculate T square separately. But if you use this procedure, right, that if you use this insight that those NSNS and RR exchange contributions are just the 2 terms in a GSO projection operator, then just calculate them separately. Yeah, and you can read out the NSNS exchange contribution and the RR exchange contribution separately. So read them out, calculate them separately. That's the answer. Calculate them.
But isn't it a statement that one of these, like if I don't put while calculating partition union, if I don't put -1 to the f, I should get 0.
No, if you put 1 plus -1 to the f, then you get 0.
I guess this is probably because I think here
No,
we
this
have-
-1 to the f is different from the DC that you are talking about.
yeah.
Yeah, that was a Gassman element, right? This -1 to the f, maybe I should have said this is the one that changes acts only on the side,
Right.
not on
I
this,
understand.
right? This is a GSO projection.
This is the x side,
Yeah,
side
this is
delta.
This is GSO operator, right? GSO operator.
But only, I guess in open string there will be only one identification left because psi and psi delta are already identified at the boundary, something like that. Or
Yeah, psi and psi delta are identified at the boundary or not at the other end. Yeah, so psi and psi delta is identified, but whether you include psi oscillators, which are when you use odd number of psi oscillators. That suppose we start with the state vacuum, okay, and let's suppose that the vacuum is invariant on the GSO. Now, are you going to allow odd number of psi oscillators acting on the vacuum or not? That's the question, right?
Right.
The full spectrum you can include arbitrary number of psi oscillators. Right? It's just that at the end you have to make sure that you only keep the one given number.
Yeah.
But you can calculate separately what will happen if you didn't use that, right? And then calculate separately what will happen if you insert a minus of there, the GSO parity. And then you add them up. Right? It will automatically project out the ones which have the wrong GSO parity. But there's no difficulty in doing this calculation without using imposing GSO parity.
Okay.
See, for correlation functions, it becomes hard. In correlation functions, if you don't impose GSO parity, then the correlation functions are not even single value.
Yeah.
Right? But for annulars, it's not a problem. Right? For annulars, you are not calculating any correlation function. So you can separately calculate what happens if you don't insert minus or 3. Okay, but this is important. This is not, I mean, we said that earlier you were talking about Grassmann, right?
Yeah.
There, the ghosts were Grassmann, right?
That is this probably standard that in paths in this calculation of partitions we need anti-periodic boundary condition.
Exactly. Yeah.
But here I guess it's something else. It's a GSO.
It's GSO, exactly. Yeah. Okay, so I think that's
So T square is done.
is very sad.
So this means we have
So this means that we have now, in principle, arbitrary amplitude. Okay, once you get T, then any amplitude now you can calculate.
because this is what you are saying that K you know now.
Exactly. That K you know now. Okay, because K is to determine now. Okay. But you have to do this for every difference separate. Different difference will have different K.
Which means different boundary conditions.
Different boundary conditions, exactly. Right? So you imagine a general given surface with many boundaries, right? Different boundaries may have different boundary conditions. And we determine the normalization factor for each boundary condition separately.
Right. But where did this thing come? The bound, is it P?
The boundary condition.
Like for this flat space DP branes, is it just P that?
Yeah, the open string spectrum depends on the boundary condition, right? How many momentum integrals you have for that.
Yeah.
Right? So that's where one place where the information is going.
But like in flat target space, I would think it's just P or is it?
Yeah, in fact, that is just exactly.
But when I compactify, it can be Y.
Exactly.
Yeah, it can be.
Even in flat target space, there are more complicated boundary conditions possible.
Okay.
If you switch on a gauge field, suppose you have switch on a constant field strength on the plane.
Okay.
That corresponds to a twisting of the boundary condition. It's a combination of normal and twisting. And that will change T, right? If you have a gauge field, if you have a brane with some gauge field switched on, then the energy per unit volume is different. Right? And so you have to recalculate that.
So this means any amplitude can now be computed.
Yeah, any amplitude can express.
What are we going to do next?
So the only thing that is left is the type 1, right? So hopefully I'll try to finish it next time. Okay. Because I have permission up to end of this month. So next Tuesday will be the last day before the end of the month.
Tuesday you will take one class.
Tuesday I'll take one. I'll try to finish the type 1.
So any classes after?
No, for now it will be over. Yeah. Afterwards I may give some lecture, but that will see. Yeah. So when do you want to take the exam?
I guess after the course.
Meaning these will not be part of the exam, right? So you can give it anytime.
Next week, Thursday.
Next week, Friday should be fine. Yeah. So you are the only one from ICT and okay, right? I think there will be some PR for students. Yeah, but for you can get this. And you have to also write something and
Yeah.
something.
So I was thinking of writing about these POs from the super events at this point.
Okay.
So there's filling the gaps. with
Yeah,
POs.
yeah.
And also there are some notes on super event services.
Yeah, exactly. And there's a paper by Wang and Yin. Right, on the where they try to get this the equivalent of the PCO as super advanced.
Right, yeah. This is 2022, right?
I think so, yeah.